And so in this unit up ahead, we're going to be looking at this idea of thermochemistry, better known as the first law of thermodynamics. Now, fancy words, I understand all of that. Really, this is the part you've been waiting for, because anytime a student hears that they're taking chemistry, the first question they always have is, oh, are we going to blow something up? Well, finally, in this unit, we will be learning all about the science behind things that go kaboom! And to help us make heads or tail of this idea of thermochemistry, we have to understand a basic physical principle of our universe. Nothing is for free. So that means every single chemical process, I'll take that a step back and I'll say any process that happens in our universe is always going to require either an input of energy, so the reaction of the process will have to absorb energy, or the reaction will release energy, right? The process will do something in which energy will flow outward. And so to help us with that, let's look at two simple examples. The first one is your typical kaboom reaction. We're going to take some propane. This is the same propane that you probably have on your barbecue or something of that nature. But we're going to take some propane, C3H8. And what we're going to do is we're going to ignite it. We're going to add oxygen to it and then add a little spark. Now, when we do that, we know that this is a combustion reaction. We, of course, produce CO2 and H2O. But now we're going to start paying attention to this new product that I have there on the right-hand side, which is when propane goes kaboom, energy gets released. And that's important because my guess is if we start to think about it, maybe the amount of propane we use will help to determine the amount of energy that gets released. So you can already kind of start to see where this is going. What's another example of this? Well, let's say that I had something like a solid piece of water, better known as a solid piece of ice. And I put that ice on my kitchen counter. Well, what do I expect to happen to that little piece of ice if I walk past my kitchen counter, I don't know, 2 hours from now? And if you sit there and tell me, well, of course it's going to melt, it's going to become liquid, H2O, I would absolutely concur with you. Because of course it's going to become liquid H2O. But the real question is, well, why did that happen? And the answer is that when I put the solid water, the ice cube, on the kitchen counter, it was absorbing energy. And as that ice cube absorbed more and more and more of that energy, then you can already know, you can already see where this is going. More and more of that ice cube melted until it completely became liquid water. Now, what's the difference between the energy in this equation and the energy in my first equation? Well, it seems like it depends on which side of the equation energy is on. When energy is produced, we say that a process is releasing energy. When energy is required, kind of like this other reactant, then we say that the reaction requires an input of energy. And this is what we're going to be looking at in this first episode as we discuss this concept of energy and how we move it from one location to another location. And so for our purposes, the way we want to think about it is that whenever a reaction requires an input of energy, so whenever a reaction is absorbing energy, we say that that is an endothermic process. Again, the prefix endo represents inward, right? If a process releases energy, so that it, like as in the propane when it went kaboom, right, that the energy was released, then we say that it is an exothermic process. So these two words, endothermic, exothermic, is how we will often describe whether a reaction was absorbing energy or whether it was releasing energy. Now, just because we're going to keep throwing these new jargon and these new terms into your vocabulary. In chemistry, whether a reaction is endothermic or exothermic, right? So whether a reaction is absorbing energy or a reaction is releasing energy. In chemistry, we refer to that as a change in enthalpy. Okay, a change in enthalpy, better known as delta H. And so what delta H represents, and I'll go into more of this in a moment, but delta H represents when it is a positive value, as in, let's say, positive, and I'll speak into terms of energy units in a moment, but if I say that something is positive 10 kilojoules, what that means is that this is a reaction that had to absorb 10 kilojoules of energy. If a reaction has a delta H, or a change in enthalpy, that is negative, meaning that we had something that released, sake of argument, 10 kilojoules, then we're going to say that a reaction dropped in energy. So if a process absorbed energy, it went up, change in enthalpy is positive. If a reaction released energy, gave energy up, then that reaction dropped in energy. And if it drops in energy, then the delta H is negative. Positive enthalpy changes, endothermic reaction. Negative enthalpy changes, exothermic reaction. Now, the first law of thermodynamics is all about solving for the change in enthalpy in a given reaction. Okay, the first law of thermodynamics is going to be all about this idea of how much heat energy was absorbed or was released by a particular process. And in a nutshell, the first law of thermodynamics states that energy can neither be created nor destroyed. Now, I know, this is an easy concept. You've heard this 1,000 times. But when I say energy cannot be created nor destroyed, what we really mean is that we're going to just move energy around. See, here's the thing about energy. If you sat there and you asked someone, well, define energy, it's actually a really hard concept to define. Because I can go back to my middle school textbook and I can see that energy was the ability to do work. I have no idea what that means. What do you mean, the ability to do work, right? Because I learned that if I put a rock at the top of a boulder, if I put a rock at the top of a cliff, right, that rock has a certain amount of potential energy. What does that mean? Well, it means that if the rock fell, then it could turn that potential energy into kinetic energy and blah, 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 blah. But I go back to the same thing. What is energy, right? And if you sit there and you tell me something like the ability to do work, I get stuck. My brain literally pops. I don't know what that means. And so our best answer, please do not quote me, is that energy, at the end of the day, is nothing more than a constant. And what I mean by that is that energy is the thing that never is destroyed. It is the thing, I'd say it like that, the thing that in any process remains the same. And the best way I could describe that is just by simply drawing here my very simple skateboard half pipe. And here's the idea. If I took my little half pipe here and I put at the top of it a ball, so here's my little ball on my half pipe. If I were to take this ball and in a perfect world, I were to just bloop, give it a little push, this ball, our expectation, is going to start to slide down, it's going to start to fall down my ramp. And the expectation is, depending on the height that I put it in at, it's going to go really, really, really fast down here at the bottom. It's going to start to slow down as it comes up, and at a certain point, it's going to make it to the exact same spot that it started at, the exact same height. And so then what's going to happen? The whole thing is going to reverse itself, right? And so what happens is that energy is that thing in this process that remained constant. So the first law of thermodynamics states that since energy cannot be created or destroyed, our universe has a certain set amount of it. Since energy cannot be created or destroyed, then the only thing we can do is we can move it around, right? And we can see how it gets transferred from one substance to another substance, or from one reaction to another reaction. And so now this is where we start to evolve the way we think about energy. What that means to a chemist is if a reaction is exothermic, releasing energy, then that means that that energy has to be released to somewhere, right? It has to go somewhere. Likewise, if a reaction was endothermic, receiving energy, then it had to receive the energy from somewhere. And the first law of thermodynamics in a nutshell is what you see down here, where it says a reaction plus somewhere is going to be the total constant energy that there is in our universe. Now, I don't like that statement. The amount of energy that the reaction absorbed or released plus the amount of energy that it got or released to somewhere gives me constant energy. I don't know what to do with that. So instead, the way we're going to think of it is what we see here. The system plus the surroundings equals our universe. Said a different way, the change in energy that a system has plus the change in energy that the surroundings have equals the total amount of energy in our universe. So, if a reaction, sake of argument, was exothermic, then that means that the system, the reaction, had a drop in energy. And as it dropped in energy, that means that the surroundings had to gain exactly that amount of energy. So what happens is that however much one dropped down by, the other went up by it, and as a result, we always get back to the same net amount of energy. And that's our first law of thermodynamics in a nutshell. And so if the first law of thermodynamics is very concerned about this idea that energy is neither created nor destroyed, that we're just going to transfer it back and forth between one substance and, between the system and the surroundings, or the surroundings and the system, whatever the case is, if the first law of thermodynamics is really focused on changes in enthalpy, I'm going to make a slight little distinction, and I'm going to say that when we talk about thermochemistry, thermochemistry is going to get a little bit more narrow in its focus, and it's going to ask the question, how much heat does a set amount of a reaction, or how much heat does a very particular case absorb or release? So thermochemistry is where we start to quantify and look at, well, if I have a little firecracker versus a big firecracker, am I still going to get the same bang? And the answer, of course, is no. So to kind of give us an idea of this, let's look at the following example. So here I have, over on my left-hand side, a match. So imagine, if you will, that I took a piece of wood, a small little piece of wood, a match, and I light it. Now, right now, what can you tell me is happening? Well, obviously, some type of combustion reaction is occurring. And more than likely, without getting too technical, as I would say that I have some wood, and I know that's not the chemical symbol or the chemical name, but whatever you want to call it, wood is reacting with some oxygen, and it's going to produce CO2 and H2O, right? Simple combustion reaction. A match burns. I could also say that because this is combustion, energy is going to be released, right? And so if energy is being released, that means that this is an exothermic process. And another way of saying that it's an exothermic process is I could say that the change in enthalpy for this reaction would have to be negative, right? Because the wood, the match, must be losing energy. It's going down in energy because I feel, when I put my hand over it, I feel the hot, 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 hot. Okay? Now, look at all the intelligent things we've been able to say. It's a combustion reaction. It's exothermic. The delta H is negative. But my question is, if I compared my little match over here on the left-hand side to my campfire that I have over here on my right-hand side, I would argue that the reaction for both of these is the same. In both cases, wood is reacting with oxygen to produce CO2 and H2O, and it is exothermic, and delta H is negative. But my guess is that if I put my hands above that campfire, I'm going to start to cook my hands. If I put my hand over the match, it'll sting, it'll be annoying, I might go hot, 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 hot. But it is not going to be anywhere near the amount of energy that was released when the campfire was burning. And so when we talk about thermochemistry, we're going to start to get into, well, even though both were the same reaction, did they both release the same amount of heat? And the answer is they did not. The match released less heat than the campfire. Well, why? I bet it's because the match had less wood, or the match had less reactant. Oh, wait a second. I see where this is going. If I have less reactants, then I make less products. And if energy or heat is nothing more than a product, you see where thermochemistry is going to go. We're going to end up with thermochemistry doing some stoichiometry to determine and answer the question, how big of a kaboom? So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.